He went to IOI camp twice in 2009 and 2010. Also, he was a coach in the IOI camp in the next year. He also went to the ACMICDC Gold Finals twice. So,
DP, language programming. Some jargon, I think must actually conceptualize this. Okay. So, just for starters, this is going to be a very basic lecture. I'll be starting from very basic stuff, doing very simple problems. So, for those of you who are kind of familiar with DP, and you'll probably find it very boring. So, I'll give you a problem which you can try on your own. So, how many of you know most of you would have seen DP probably before. So, those who are confident in DP, just try this problem. So, it's called dominating set on trees. So, how many people know what dominating set means? Okay. So, dominating set is as follows. You are given a graph G with vertex and E. A vertex subset S, which is a subset of E, is a dominating set. If you take the close neighborhood of every vertex in S, that is, you take every vertex in S, take all its neighbors, take this vertex also, take this union amongst all these vertices in S. So that's called close neighborhood, and you represent it as N of S. So N of S is basically U such that U is a neighbor of a vertex in S, or U is in S itself. Union of these two. So S is a dominating set of this graph G if neighborhood of S is the entire vertex set itself. Okay, this is called a dominating set. Now I want you to find the dominating set of a tree. Given a tree, find the dominating set, minimum dominating set. So do this with polynomial. So this is a DP problem. Those of you who find this lecture very boring, most of you will probably just try this on the side. Now coming back to actual lecture. So what is DP? DP is just some paradigm. You're using multiple paradigms. You're using 3D. Using divide and conquer. Using this graph searching. Using multiple searching. So this is some another way of solving problems. It's not a concept as on its own. There is some theory behind DP, but it's kind of hard to explain just the theory. So what we do is we just take some problems. We'll start with some very simple problems. We'll see how to solve them, and then we'll analyze what is the common hidden structure behind those solutions. And that is basically what DP will be. So we'll come to what exactly DP is only after some half an hour. Because then we just solve some simple problems without any agenda. We just try and do problems. So the first problem we take is the problem which was the first Princess Frida. So how many of you were able to solve this? How many of you got it accepted? How many of you think you have the solution? Like maybe you didn't code it, but you think you know how the solution is. Right. So the problem is like this. You are given an array of integers, positive integers. You have an array A. This equals 1 index. So you have a n size array. All of these are positive integers. A1, A2. And what you have to do is you have to pick some of these such that you don't pick any two consecutive elements. You have to pick a subset of these elements, but you shouldn't pick any two consecutive elements, and you want to maximize the sum. That is the problem, right? I mean, that's a huge story, but everyone sees that this is the problem as such. Right? Does anyone have a problem with why this is the problem? is find S. S is a subset of 1 to n, such that there are no negatives. Blah, blah, blah. Fine, clear? Yeah. So, what are some? Do you think any greedy solution will work? Did anyone try a greedy solution? What is one natural greedy? Alternate. Okay. So you pick alternate. Pick 1, then pick 3, then pick 5. Or pick 2, then pick 4. That is one greedy. Just choose the maximum of these two and output them. Why won't that? Okay. So that's one possible things. Alternate. Some other greedy. What is you want to maximize the sum? So what about just picking the maximum first? Then picking the maximum with next maximum, which is possible. But say if the first two maximums are next to each other, you can't pick the second. Pick the most maximum, then look at where the second maximum is. If it is adjacent, don't pick it. Always pick it. Keep doing this. This is like a very kind of natural greedy implementation. Did anyone try this and try? Greedy pick. Okay, so we just see why these two don't work. So it is to the fact that this one, neither of these will work. So can someone give a counter example for the first one?
100, 5, 6, 200.
100?
5, 6, 200.
So what is the actual answer for this? It's this. But taking this and taking this, neither of them are. So this. And for the second one?
5, 8, 1, 9, 10, 6. 5, 8, 1, 9, 10, 6.
Okay. So what is the greedy second one? You pick n first. Then you can't pick 9. Then you pick 8. Then you can't pick 6. You can't pick integers after this. So this is 18. Greedy gives 18. But what is the actual answer?
10.
What is that?
5, 9, 6.
8, 9, 6.
8, 8, 9.
Kind of fun. Do you see what's happening here? Why doesn't this work? Here it was easy to see why this algorithm doesn't. What was the actual structure which messed up the answer? Like, give a simple explanation. It's kind of weird. Do you immediately see why this doesn't work? This seems like a feasible solution. You see from this example why it doesn't work. I can't figure out why. This is a much more simple example. Just say take 5, 6, 5. The maximum is 6. Obviously, you can't be continuous, but the best is 5 and 10. This is kind of the blocking structure. Again, when you pick 10, the actual answer contains both 9 and 6. But because you pick 10, you can't pick this. That is the block, main. See the difference between the actual answer and the greedy answer. It's just, this is 9. Here, both 9 plus 6 was greater than 10. So, some two elements which differed by 1. Their sum was more than a middle, but the middle was picked, so you don't pick this. So these are some two feasible greedies which didn't work. What else? What other approaches do you try and fail? Not the accepted solutions. Did someone else have any other solution which failed? So this basically just says that this algorithm doesn't have a very nice structure. There's no obvious structure to go work with. Many programs, if they're greedy, there'll be a very nice structure and you just follow that, you'll get it. That's how greedy solution. But DP in a way is kind of searching over all the alternatives, and you search it in a structured way. That is kind of one essence of what heap is. That is what we do here. What we do is we look at all the alternatives and we kind of partition the alternatives in these equations. What we do is we look at subproblems. This is inherent to all DB problems. You'll be working with subproblems. So here the full problem is working with 1 to n. A subproblem is a problem of the same nature but in some restricted space. This is not a formal definition, usually we do this. And what is some natural subproblem here? Just look at some prefix of this. So what you do, you ask, okay, I don't want 1 to n, just take the first 5 elements, and within this 5 elements, what is the maximum n? You ask this question. Suppose you can do this for everything in some way, and then finally this amongst all n, what is the best n? So this won't work. Let's try to do and see. This definition will not be enough. Easy. So what you will want to start with the smallest subproblem, right? So the smallest subproblem is this 1. So okay, let's kind of make something. So let's try subproblem of I is the best we can do restricted to a of 1 to I. So what the final answer should be? Sub of n. Clear, right? If we can find sub of n, that is the final answer. What is the best we can do from 1 to n? We want to get to sub of n. But we start with something which is tractable, which is very easy. It is sub of 1. What is sub of 1? What is the best you can do with this one element? What is the best? It's all positive, so you take it. So sub of 1 is just a of. What is sub of 2? Max of a. What is sub of 3? So it's either A1 plus A3 or it's A2. So it's max of A2. Max of A2 or A1 plus A3. What is sub 4? What is sub 4? One, three, two, four, one, four, one. There are 3 different options. But this seems very tedious. I mean, like, you see some structure to this. Now, what if I ask 5? 1, 3, 5, 2, 4, 1, 1, 4, 2, 5. Like, it's not possible to enumerate all these. So what you want to do is you want to use something you already know. You want to compute sub 4 using what you already know. Try to do it. Can you do something? So sub 4 is these 3 options. Can you get those 3 options somehow using these? Maximum of 2 plus 4. What's sub 3? Why is that? Okay, you're saying sub 4 is max of A of 2 plus So here what is it? You see, sum of 4 is sum of 2 plus a of 4 or sum of 3.
Whether I need to include this particular item in this subset for maximizing or till I minus 1.
So what you see is exactly as 2 options. Look at all the different possibilities, all the different alternative subsets you can. Either 4 is in the subset or 4 is not in the subset. There are only two all alternatives. There are only two options. Either 4 is in S or 4 is not in S. Now, if 4 is in S, then I know 3 is not in S. Because I've chosen 4, I cannot choose 3. Now, the subproblem just boils down to finding the maximum in 1 and 2. So, whatever is the maximum in 1 and 2, I can take that maximum and then take 4. We do this in a different way also, but this is some overview. All the other possibility is 4 is not in S. So, I can just delete 4. And now I already know what is the best between 1, 2, 3. That is stored as something. That is something. So, that is this option or is this option. So, I take a maximum of these. So, this is a perfectly valid choice. Let's try to make this a little more structured. So, the definition of sub was the proof required a little thinking. Okay? It was not a very easy. Let's make life very simple. So what we do is we redefine the value of sub, the definition of sub, and we say we define a new meaning. Let's call it sub include. So sub included of I is the best you can do between 1 and n. But you also add the constraint that the ith element should be picked in the set. So you have this added constraint. So include of I is best we can do in 1 to I with I in S. You have this extra constraint. So like sub of S was just B. Sub of 4 could be or 4 couldn't be. But now we are putting this extra constraint to make, you will see why the proof kind of becomes easier. This will be generalized further. So that's my definition of sub, include of I. So what is the final answer? Suppose I found sub include of I for everything, from 1 to n. What is the final answer? But maybe that also requires one small observation here. So maybe speaking, in the subset, the final optimal subset, there will be some element which is picked, which is the last element. Okay. So that will be the optimal for that sub included. See, if my optimal solution pick this, and this, and this. This was the 8th element. Now sub included of something of 8 will be this answer. Okay. This set which is chosen will be the optimum for sub included of 8 because 8 is included in it. Okay. So I can just loop over all the sub included, take the maximums, and output that answer. Now what he said was I just take sub included of n, sub included of n minus 1 and take the maximum. Why is that? So now before getting this up, let's look at some structure of the problem. So first I make a claim. See, what was the kind of vague reasoning behind that first alternative thing? So the main thing which you think is, I know that I can't pick 2 consecutive. So maybe when I take any 2 consecutive, one of these 2 will be picked. Is this true? I pick any 2 consecutive elements it's not true, give me a complete one. We already had 105 is to 200. You pick these two are not. That's a complete number. So that claim is not. Now I claim something else. I pick any three consecutive elements and I consider any three consecutive elements. I consider I plus 1, I plus 2. Is it true that at least one of these three will be picked in the solution? I know that if I consider consecutive 2, that claim is wrong. I think I consider any consecutive 3, will at least one of them be in the solution. Why is it? But maybe I can't pick this because maybe I will pick I minus 1, maybe I will pick I plus 3. I have some constraints. Exactly. See, suppose I and I plus 2 are not picked, then I can pick I plus 1. That's simple. Okay. So if I and I plus 2 are not picked, I will pick I plus 1 and my solution increases. So the formal proof will go as follows. Suppose there is an optimal solution in which there are three consecutive elements which are not in the solution. Then I know I and I plus 2 are not picked, so I can pick I plus 1. So my solution increases. So what I consider to be optimal solution is not an optimal solution. This is a contradiction. So the assumption that there are three elements which are not picked is false. So we prove the claim that for any three consecutive elements, at least one of them will be picked. But it's just not, it's only at least one. It's not exact one because maybe I pick I and I plus 2. So it could be 1 or for any three consecutive elements, I pick 1 or 2 elements. So this is some structure to this problem. So now coming to this claim. This claim was amongst the last two elements, at least one will be. Is that clear? Wait. Give me a formula. The claim is this. Consider n minus 1 as n. Amongst these two elements, at least one will be picked in any optimal solution. At least one of these two elements will be picked. This was his claim. Now, why is this? No. I gave a formal proof. Give me a formal proof along those lines. I get what you're saying. I just want you to formally state what was it. Okay. So in this n plus we get n plus 2 doesn't exist. But n plus 1 doesn't exist, sorry. Okay, so how do you modify this proof to get that proof? Like, what is the is it clear to everyone? It's this. Suppose both the last two elements are not picked. I can pick the n then because the n minus 1 is not picked, I can pick it. You get the same coordinate. Here I can pick I plus 2 because I plus 2 might be picked, but there is no n plus 1 to have already been picked in the solution. So I can pick. If n minus 1 is not picked, I can pick n. So this claims that either n minus 1 or n will be picked. So I don't need to go with all the elements and take the maximum of subbing. I just need to take subbing of n minus 1 or n. Because I know that any optimal solution will pick either n minus 1 or n. And picking n minus 1, all those options will be covered in subbing of n minus 1. Picking all those will be covered in subbing of n. So now all I need to do is figure out how to do subbing of I for all n. So now what is subbing of 1? What is subbing of 1? A1. Subbing of 1. It's not match of A1 A1 because I need to pick the second element. Because I pick the second element, I can't pick the other, so I have no option. Just A1. What is subbing of 3? A1 plus A1. I don't have each one. What is subbing of 4? So subbing of I can write it to A of I and write it. So it's A of I plus 1. That is the question. What is this? Subbing of 2. Now look at this comparison that we had. So, yeah, so it's max of subbing of 1 command. But let's think of what we want. Like, this is true. The algorithm will go through, but let's try to constantly think of what we want. What is subbing of 4? I know I have to choose the 4th element. This is the only constraint. And this constraint forces me that 3 can't be big. So now, in this 1 to 2, it's again the subproblem. But now the subproblem is without the constraint that 2 should be big. So now it is going back to sub of 2. Okay. So all I'm saying is subbing of 4 is a of 4 plus sub of 2. But what is sub of 2? Sub of 2 is max of subbing of 2 or subbing of 1. In other words, take any, forget about sub, we are only working with subbing. Now take any subbing of I. I know subbing of 1, I know subbing of 2, I know the subbing of I. But now I want to get sub of I. So sub of I is just that it's from 1 to I, but now I don't have the extra constraint that I should be big. I don't have the constraint. So now what is it? So now you use this claim again. Now it's a subproblem. I know that either I or I minus 1 will be picked in any optimal solution in this. So now I can forget about I plus 1 to n. It's just this subproblem. So this subproblem is same as the problem we solved. We are trying to solve. And in the problem we are trying to solve, we know that either n or I minus 1 will be picked. So take the same argument in either I or I minus 1 will be picked. So sub of I is just max of subbing of I, subbing of I minus 1. So I have this. So now what is subbing of 4? It's a of 4 plus sub of 4. Because I have to pick 4, I can't pick 3. Now what is the best I can do from 1 to 2 without any constraint, which is sub of 4. Okay. So what is it in general? Subbing of I is what? A of I plus sub of I minus 2. Where sub of I. So first I compute sub of I, subbing of I, then I compute sub of I. So what is sub of I? It's just max of subbing of I, subbing of I minus 2. And I have some base cases. So let's actually go over the base cases. But the base cases are exactly the same thing. You just need to do it for. So let's go. So